Okay, number 15 is asking us to graph the function, identify the y-intercept, the asymptote, state the domain and range, and whether or not the function is increasing or decreasing. So letter A is y equals 4 to the negative x. And the first thing I'm going to do is notice that my exponent has a negative power. So I'm going to rewrite this as 1/4 to the x power. Now I know because my base, because remember all our exponential functions go a times b raised to x. B is our base. Because this b value is less than 1, I have a decay function. Now I could put some numbers in here, like if I put x is 0, anything to the 0 is 1, and my decay function looks like this. I know it has an asymptote at y equals 0 because our general format is going to be a times b raised to x minus h plus k, and y equals k is going to be the asymptote, and that's going to be a horizontal asymptote. If I wanted to get super fancy, I could pick up my calculator and go to y equals and put in 1/4 raised to x, or I could even just put in 4 raised to negative x. So we've got 4 raised to the negative x, and we're going to go look at our graph. And sure enough, there's our decay function. And if we need more points, we can go to our table, second graph, and those are some big numbers. And there are some numbers that are a little easier to graph. And there's a point I did 0, 1. And you can see that it trails off and starts to get really small. Remember, this is just scientific notation, is if I move the decimal point 4. So, going back to our properties. We have the asymptote already. The y-intercept we have is 1. So, y-intercept is 1. So we have a y-intercept of 1. We also need the domain and the range. Well, we can see that the graph covers the whole x-axis from left to right. So we know that the domain is going to be all real numbers. The range is going to be everything above 0 because the graph comes down and runs against the asymptote. So it's going to be y is greater than 0. Is the function increasing or decreasing? It is decreasing because it is a decay graph. And we want to also know that it is decreasing on the interval of all real numbers. Alright, letter B is y is 4 raised to x plus 3. Because our base is 4, we know that this is going to be a growth function. So greater than 1 base, it's going to be a growth. And here we have a k value of 3, so we know immediately that we have a horizontal asymptote at y equals 3. So I'm going to go ahead and make my graph. That's terrible. And 1, 2, 3. I'm going to put like a dotted line there. And now I'm going to look for my y-intercept by putting 0 in. And I have 4 raised to 0 plus 3. Well, anything raised to 0 is just 1, and then 1 plus 3 gives me a y-intercept of 4. And this is a growth function, so I have a point here, and my asymptote comes up from the asymptote. Or my graph comes up from the asymptote. So we know our y-intercept is 4. Again, we put 0 in for x. 4 raised to 0 is 1. The domain is still going to be all real numbers. The range is going to be y is greater than 3, everything above the asymptote. And this is an increasing graph on the interval of all real numbers. Our last function is 2/3 raised to x, and we know that 2/3 is going to be a decay function because 2/3 is less than 1. We know we're going to have an asymptote at 0, again, because there's no k value. So if I was like, I'd be like So there's my asymptote at 0 if I needed to put it in there. And I need some points. I know it's a decay function. I'll put 0 in for x. That way I can also get my y-intercept. And guess what? Anything raised to 0 is just 1. So once again, just like A, I have a y-intercept of 1. This graph is pretty similar to A. It's going to actually have the exact same properties. So we've got a y-intercept of 1, we said. We have an asymptote of y equals 0. We have a domain of all real numbers. We have a range of everything bigger than 0 because it's everything above the asymptote. And once again, we are decreasing on the interval of all real numbers. Number 16. In 1900, the population of a town was 5,000. The population increased at an average rate of 2.5% a year. What is the population to the nearest whole number in 1920 and 1950? Well, the first thing I want to do is write a growth function. To write my growth function, I'm going to start with my initial value. And it's good because it's a growth function, it's going to be 1 plus my rate as a decimal. So it's like 100% plus 2.5%. We write 2.5% as 0.025 and raised to x for the number of years since 1900. So, what is the population for letter A in 1920? Well, that's going to be 20 years from 1900. So on my calculator, I'm going to go 5,000. And I know that this is going to be 1.025 because, 1 plus 0.025. And then to the 20th power. And I'm going to grab my handy-dandy graphing calculator. Type that in. And get about, let's see. So, let's see, 0.025. Hey, come on. There it goes. Close parentheses to the 20th power. And that gives me, well, I want to round that to the nearest person, because that would be weird. You don't want to have 0.08 of a person living in your town. That would be disgusting. So, it was at 93. Alright, now for B, I'm going to do the exact same thing, but now I'm going to have an x value of 50. So, letter B is just going to be, on my calculator, 5,000 times 1.025 raised to the 50th power. And again, I'm going to round to the nearest person. And when I type that in, I'm going to get about 17,185 people. An account pays 4% compounded monthly, number 17. You deposit $6,000 into the account. You do not deposit or withdraw any money from the account. How much money to the nearest cent will you have in 5 years? Well, the first thing we want to do is remember our formula for compound interest is the amount is going to equal the principal times 1 plus rate as a decimal divided by n raised to the nt. Okay, remember P is the principal. R is rate as a decimal. N is the number of times compounded per year. And T is just years. So, we're going to have A equals 6,000 times 1 plus 0.04. Well, this is compounded monthly, so obviously 12 months in a year. And then raised to the 12 times 5. Alright, now when I type this in, the first thing I want to do is if I don't know what 12 times 5 is, I'm going to do 12 times 5, which is 60. So now I'm going to do 6,000 times 1 plus 0.04 divided by 12, close my parentheses. Whoop, I'm missing a 0. Not good. Put that in there. And I'm going to raise that up to the 60th power. And I'll get 7,000 to the nearest cent. We've got $7,325.98. Alright. A luxury car costs $75,000. It depreciates at a rate of 25% per year. So we're going to write our function as 75,000 and then 1 minus the rate. Now remember, for our population problem, we did 1 plus the rate because it was appreciating, it was growing. This is depreciating, it's a decay problem. So 1 minus 25% per year, and we'll make year x. So there's our function. So letter A, what will the car be worth to the nearest dollar after 5 years? So we'll do 75,000. And I happen to know that 1 minus 0.25 is 0.75. If you wanted to leave it as the other way, that would be okay. And to the 5th power. And we're going to put that into our calculator to the nearest dollar. That would be 17,798. Part B says, what will the car be worth after t years? I have to tell you, I think it's kind of dumb. They should have asked that as A, because we're just going to give our formula raised to t. It's silly. Alright, number 19. A town has a population of 250,000 due to job losses in the area. The population of the town decreases, decay, at a rate of 5% per year. Write the exponential model. No big deal. We've done this before. We did it with the last problem. We're going to have y equals 250,000 times 1 minus 0.05, or you can make that 0.95 raised to x. The end. What is the expected population in 10 years? So we're going to go just put 10 in for x. And again, you should make that 0.95, I guess. To the 10th power, I'm going to grab my calculator. I'm going to round to the nearest person because that would be weird. Alright, number 20. You deposit $1,000 in an account to save money for a car. The bank pays 7.4% interest. If you deposit 6 years, compounded, continuously. We are not going to use the formula we used for number 17. Now we are going to use the formula amount equals principal times e raised to the RT. Continuously means you're basically getting interest all the time, every second. So if we took the limit as n approached infinity, what would happen to our other equation? It would turn into the number e, and the rate would kind of pop out into the exponent. So complicated explanation, easy problem. The rate is 0.074 times 6. Grab my calculator, and we're going to have 1,000. Now I'm going to use second ln. There's my E button. And isn't that nice? They give you a parentheses. And we can see that we are going to have in the account $1,558.93. Number 21. Graph the function. State the y-intercept, and all kinds of exciting things. Alright, well, obviously the first thing I'm going to want to do is type that into my calculator. I do know a couple things, though. I want to remember that E is a number we know. E is just the number 2.7, and then there's, like, stuff. 2.7 would be a growth function. However, we have a negative exponent here, and that's going to turn that into a decay function. I want to know that because that way when I look at my graph, if I don't see a decay function, I'll know that I made some kind of typo. So in y equals, I'm going to do e to the negative 2x. And there's my decay function. I can see that I have an asymptote. I'm going to write that down right now. Y equals 0. To find my y-intercept, I could put 0 in for x. That would give me 1. Or I could just look at my table And sure enough, 0, 1. So y-intercept is 1. The domain is going to be all real numbers because this graph went from left to right. The range is going to be a y is greater than 0 because it's everything above the asymptote. Oh, I should probably make the graph, huh? There's my nice asymptote. Alright. We did the asymptote, we did the y-intercept, the domain, the range, increasing or decreasing. Well, this is a decreasing function. And we also want to make sure that we know that it is decreasing on the interval of all real numbers. Number 22. In a bacterial culture, the number B of bacteria present is modeled by, and if you can't see because it's too fuzzy, or for some reason you don't have your exam review packet and you're just watching these videos, for fun, because that's what you like to do with your free time. That's what I like to do with my free time. Not really, but whatever. Alright, on task, Ms. Strauss. We've got 0.03 raised to t, that's what that exponent says, where t represents the time in hours since noon. How many bacteria are present at 5 o'clock? Well, 5 o'clock, 5 hours have gone by, so it's calculator time. I'm just going to straight up put in t is 5. A lot of stuff here. So 1, and then I'm going to use my handy dandy E button, times 5, and that's how many bacteria there are. So the answer to A is 6. I'm going to round to the nearest bacteria, because that just makes sense to me. Alright. Part B says, how long, correct to 3 decimal places, will it take for there to be over 120,000 bacteria? So what I'm going to do here is I'm going to say 100 for B, 120,000 equals 15,000 times e to the 0.3t. And I'm going to divide by 15,000. Oh, too many zeros. So let's see. These zeros are gone. These zeros are gone. These zeros are gone. So it's 120 over 15. On my side calculator, 120 divided by 15 is 8. Beautiful. So now we just have 8 equals e to the 0.3t. What we're going to do is we are going to rewrite this as a logarithm. Some of you like to use what we called in class the Roman numeral 9 rule. To use the Roman numeral 9 rule, the exponent had to come first. So I'm going to switch colors here. I'm going to rewrite this as e raised to 0.3t equals 8. And then we went and it was ln, because it was log base e of 8 equals 0.3t. Now I can do ln of 8 on my calculator. Ln of 8. So that is that number. And then I'm just going to divide by 0.3. And I get, to correct to 3 decimal places, I get t equals 6.931. Do I have a unit here? What did it say? Hours? I think it was hours. T, hours. Yes, time in hours.